Well, first of all, thank you all for being here, and to Jens for inviting me. It's a real pleasure. I myself am a philosopher. I'll come out of the closet right away. I have given talks to fellow philosophers and logicians, to linguists, historians, art historians, lawyers even, computer scientists. But I think this is the first time I'm talking to an audience that consists primarily, or I think even exclusively, of mathematicians. So I'm really curious to see how it'll go. It's going to be about my project on logical geometry, on Aristotelian diagrams, which, as you can already hear from what I said before, is very multifaceted. What I'm going to be focusing on today is, of course, the most mathematical, especially the most algebraic part of that project. So, as you might have read in the abstract, I've divided the talk into 4 parts. The first 2 are more introductory in nature. They correspond to existing work. The last 2 correspond to really ongoing research. The first part is about what I have called historical and philosophical context. It's basically the part that I could give without any change also to an audience of linguists or lawyers or what have you. I did explicitly want to keep this in today because later in the talk, the idea is going to be that we're going to be studying the mathematics of Aristotelian diagrams. We're going to be building a mathematical theory. Before we start doing so, I think it's important that we know what it is exactly that we are building a theory of before we set out to do so. Then I'll say something about Aristotelian diagrams in the context of Boolean algebra, existing work. And then I have 2 parts on the one hand, logic sensitivity and Bitstring semantics, and on the other hand, categories of Aristotelian diagrams, which are both really ongoing work. I should warn you, I have brought probably way too much, so we'll have to see what we can cover. But ideally, I want to cover both 1 and 2, and then a nice selection of 3 and 4, but we'll see how far we get. Good. So, historical and philosophical context. This is a talk about algebra of Aristotelian diagrams, so I should start probably by saying what Aristotelian diagrams are. An Aristotelian diagram is, you could say, a visual representation, and that's why we call it a diagram, of a couple of objects, which can be sentences from natural language or formulas from some mathematical language or programming language, even sets, whatever, and certain logical relations holding between those entities. These relations were for the first time studied by Aristotle, who we can see over there, and that's why we call the diagrams Aristotelian diagrams, although I should say Aristotle himself never drew an actual Aristotelian diagram. He was only talking about the relations. For now, very informally, we say, for example, of 2 sentences that they are contradictory to each other, even only if they cannot be true together, and they cannot be false together either. We say of 2 sentences that they are contrary if they cannot be true together, but they can be false together. Subcontrary means that they can be true together, but they cannot be false together. And then the one that you might expect if you have a combinatorial mind would be they can be true together, they can be false together. That's the 4th one that you would expect. I'll come to that at the very end of the talk, actually. But the 4th relation that we're interested in is typically subalternation or logical implication, logical entailment, basically, which means the first sentence entails the second one, but not the other way around. Okay, so these are the relations that the entire talk is going to be about. The most basic example, the oldest example also of an Aristotelian diagram is the square of opposition. In a contemporary visualization, it looks like this. For example, we say that all humans are rational and no humans are rational, that these 2 sentences are contrary to each other because they cannot be true together. Note that I'm assuming that there exists at least one human, existential import as we call it in logic. If there are no humans, then they can be true together. So these 2, on the assumption that there is at least one human, cannot be true together, but can be false together. Okay, for example, in a situation in which some humans are rational and some are not. Okay, and in this way we have all the relations that you see over there. 4 sentences, 6 Aristotelian relations holding between them. This is the nice contemporary version of the square of opposition. Remember, this is a part of the talk that I could also give to historians. You'll see why now. If we look at this kind of thing in the actual manuscripts, centuries old, we don't see this, we see this. Okay, So we find these diagrams where it says, for example, omnis voluptas bonum est, every desire is good, some desire is good, and so on. And what you see here, contraria, subcontraria, or maybe you don't see it, but it literally says here subcontraria in Latin, if you can decipher it. This is a diagram, 2nd century after Christ, Apuleius. If you studied Latin in high school, you might also know Apuleius from his novel, The Golden Ass, Metamorphosis. Here's another diagram in Greek. I really also want to emphasize the intercultural dimension here. So this is from a Greek author, Ammonius. For example, here we have, this is the manuscript version, but my paleography is so bad that I really wanted to give also the nice typographical version. And here we have, for example, pas anthropos peripate, so every human walks, etc., etc. Also in Arabic, I don't know Arabic, so I'm just going to show this to you. I'm just proud that I can show this. It looks nice. I have a PhD student working on this, by the way. He's Persian, Iranian himself, so he can read this. Now to languages that we do understand. German. So this is the first known diagram, the first known square of opposition in German. What I think is interesting here is, this is a side interest of mine, how these words of contrariety, subcontrariety, and so on, how they started getting rendered in contemporary languages. I think German is a really interesting case because, for example, contradictory, the relation of contradictory is translated into German as tödlich, deadly. Subcontrary, feindlich, vijandig, enemy-like. This is the first one in English, and this is the first one in Dutch. Printed, especially because we're in Antwerp, I should emphasize by Plantin, Christophe Plantin. So it says here, for example, alle geleerdheid is nut, enige geleerdheid is nut, all science is useful, some science is useful. Note, by the way, that contrary and subcontrary are translated as rechtstrijdig, strijdig, so again, battle and so on. And here, onderstrijdig. Onderstrijdig because subcontrary, okay? Good. So thus far, all I've shown you are squares of opposition, a very simple diagram just in a couple of languages. I don't want you to go away from this talk thinking that I'm only interested in squares of opposition. There are many other more complicated diagrams. For example, this one, which has 8 vertices in total. In each vertex, we don't find a single sentence, but 9. And you can perfectly explain why it has to be 9. I don't want to go into the details of this, but again, I want to show you later on when we will be developing a mathematical and algebraic theory of Aristotelian diagrams. This is ultimately what I have in mind when I'm talking about all of this. Okay, so keep that in mind when later we're talking about adjoint functors and so on. Good. This was the historical part. One final thing that I want to say in this introductory section is, if you look at Aristotelian diagrams today, we still see that they are used a lot in philosophy and logic, but also in many other disciplines. Also disciplines where you might not immediately expect them to occur. For example, political science, legal theory. Here you see yet again a diagram that is more complex than just a square. Here one from linguistics, if you want to explain the rhetorical effect of litotes and the idea of are you happy? Well, I'm not unhappy, that kind of thing. If you want to explain what's going on there, people have used extensively Aristotelian diagrams. In computer science, you see that all of a sudden we have the typical LaTeX computer modern fonts. So we also have them there in knowledge representation formats. Yeah.
For example, in previous slide, when we say not unhappy, is this kind of referring how in rather, well, in formal logic, this would be equivalent, happy and not unhappy, because you have the elimination of the negation, but here that doesn't happen.
Yeah.
Is this formalizable?
Yeah, absolutely. Yeah, absolutely. And because you don't, and the idea is that unhappy is not a contradictory of happy, but merely the contrary. So that's why not unhappy doesn't cancel, the two negations don't cancel, and it's not equivalent to happy. You could make this easier by saying, why are happy and unhappy contraries? Well, they cannot be true together. A person cannot be happy and unhappy at the same time, at least if it's a rational person. but he can fail to be happy and unhappy if he's in a kind of neutral state. Okay, happy and sad would be a maybe even better example, but that's not the one on the slide, of course, because yeah, then it's not about litotes. Good. Similarly, okay, if you can.
Okay, no.
Okay.
Sorry.
Good. This is actually from computer science, but basically this has to do with topology. It has to do with interior of a set, closure of a set, and the boundary of a set, of an open set. So you can also see that, but I don't really want to get into that. These are just examples. Another thing that I also wanted to highlight is one of the things that we have been working on quite extensively is a database. So I don't just want to give these 5 or 10 nice examples that I give in every talk at the beginning of every talk like this. I want to study all Aristotelian diagrams, also the less interesting ones. So that's why we are building this database, the Leonardi database. Leonardi stands for Leuven Ontology for Aristotelian Diagrams. It's an ontology in the computer science sense of the word, namely a vocabulary for describing these things. And at the moment, you can see that there are over 3,000 diagrams in the database, and it's still growing quite rapidly, I should say. So if you want, you can have a look yourself. All the diagrams that you see on the slides today are in there, and 3,000 other ones as well. Good. So, final question that I want to ask in this introductory part is why? Ultimate philosophical question. Why study this? Why should we be interested in this? Why are Aristotelian diagrams used so widely in the first place? Both historically across time periods, but also today across various disciplines. The standard answer is because they are very useful pedagogical tools. They are useful for teaching the abstract discipline of logic to typically stupid students. Keep in mind, a lot of what we are talking about is medieval logic. In medieval times, you go to university at the age of 12, not the age of 18, right? Lives were shorter, so yeah, the entire education was shorter. So you have to keep in mind, if you start studying logic or maybe algebra at the age of 12, yeah, then maybe a nice little diagram in all its completeness might help. Okay, so they were pedagogical tools used in the teaching of logic, designed to facilitate the recall of knowledge that students already had. So it's not about creating any new knowledge, it's just about remembering stuff. Okay, I don't think that's the whole story. I don't think it's wrong, but I don't think it's the whole story. Why? Well, because this cannot explain that Aristotelian diagrams nowadays are found primarily not in textbooks or so, but really in research level papers, encyclopedias, reference works, and so on. I would say that they are used so much, especially today, because they are powerful heuristic tools. They do help to create new knowledge, okay? Namely by allowing us to draw high-level analogies between seemingly unrelated frameworks, one from computer science and one from legal theory, for example. And in that way, you can then introduce new concepts from one discipline into the other. The quote that I've given here is not a quote from a paper, but just the title of the paper, because it exactly summarizes what I have in mind. It's the title of a paper by Chuchi, Dubois, and Praat, and they say, well, look, we present here a structure of oppositions in rough set theory on the one hand, basically topology, and formal concept analysis on the other hand, towards a new bridge between the two settings. And the beautiful thing, of course, of a bridge between two settings is once you have a bridge, it allows for two-way traffic between the two settings. Okay. So I think this is a much better answer, especially for the use of Aristotelian diagrams today, but not only today. Okay. So I want to end again with a historical example from Jacques Lefebvre d'Étaples from the 16th century. And he says, for example, well, look, this square over here is analogous to this square over here. Note that the square here is one between sentences. Every man is white, no man is white, and so on. And here is between individual words or sets, if you like, white, black, not white, not black. And so this is going more in the direction of hot and cold or happy and sad, as we were talking about before. So this idea of analogies, heuristics, also has historical roots. Good. So this by means of broad philosophical introduction. If you want to start studying this mathematically, I think the right setting is that of Boolean algebra. Okay. Maybe one slide to give you some context specifically about this mathematical study. So we have this huge diversity of Aristotelian diagrams across time periods, across disciplines. They are used a lot for teaching purposes, for heuristic purposes, and so on. But the idea is always they are used for a reason external to the diagram itself, if you see what I mean. Be it teaching logic or finding new parallels across disciplines, but it's never, the diagram is always a tool, and just a tool, you could say. What we do in logical geometry, which is the name of the research program that I've been working on for maybe 10 years now, is to study these diagrams in a more systematic fashion. Okay? So we don't focus on the details of this or that specific historical diagram or diagram in computer science or whatever, but we focus on these diagrams as objects of independent interest, okay? Regardless of any specific purpose that they may serve. And this comes in several flavors, if you like. We do this in several ways. Many of them mathematically inspired. I will be focusing on the logical and algebraic aspects, but there are also philosophical aspects, cognitive aspects. For example, I collaborate with people who do eye tracking studies on how people work with diagrams when they solve a problem, for example, and so on. But now you really know the broad picture, okay? What we are going to be doing today is the logical algebraic side of the broad research program of logical geometry. Good. So what we think is the best framework for studying Aristotelian diagrams in a mathematical setting is the framework of Boolean algebra. Okay. So we take a Boolean algebra. I assume everybody knows what a Boolean algebra is. More or less, yeah, basically think of a power set of a set and you're good. And so if you have a power set, you can take intersections, unions, you can take complements. The empty set is always in the power set, and the entire set that you're taking the power set of, bottom and top element, if you like. As far as I'm concerned, you're good to go. If you understand this, you're good to go. Good. So we say that two elements of our Boolean algebra are contradictory if their meet, their intersection, if you like, is the bottom element and their join element is the top element. Contrary means that their meet is still the bottom element, but their join is not a top element, and so on and so forth. So these are the mathematical analogs of like the very first slide, if you remember. Okay, now it's no longer about they can be true together. Like as a philosopher, I would ask, what do you mean with true? What do you mean with can? And so on. Now these questions don't arise anymore. Okay, these are just questions or just definitions in a Boolean algebra. Yeah, maybe just for reference. In general, this is called meet and this is called join. I will be using these words a lot also in logic, conjunction and disjunction, but again, you can also think of them as intersection and union in a set theoretical context. The Aristotelian relations will be called AR for the Aristotelian relations for a Boolean algebra B. Okay? And the beautiful thing is we can now look at these relations by simply plugging in concrete Boolean algebras for this parameter B, if you like. For example, we can look at the Lindenbaum-Tarski algebra of a concrete logical system S, or we can take a power set. That's the example that I was already getting at, if you don't really know what Boolean algebras are in full generality, and even some more interesting cases. So I now want to run through these examples. Okay, so let's say that we are working with a logical system, propositional logic, predicate logic, nothing really fancy. I assume that it has Boolean connectives and that it has a model theoretical semantics. The Lindenbaum-Tarski algebra of that logic is basically the quotient structure of the language, the object language of my logical system divided by the equivalence relation that is logical equivalence. Okay? So what do? Well, we look at all equivalence classes of formulas phi, where equivalence class just means a set of all sentences that are logically equivalent. So for example, in the equivalence class of P, you're going to find P, but also not P, and P or P, and P and P, and so on. So all formulas up to logical equivalence are in this algebra. Okay. And now we can say, for example, that two elements of the algebra, that is two equivalence classes of formulas, are contrary relative to the Lindemann-Tarski algebra of S, if and only if, well, apply the definition, their meet should be the false-sum element, should be the bottom element, and their top should not be identical to the top element of the algebra. But of course, if you know how to calculate meets and joins in Lindemann-Tarski algebras, it basically just means, well, the meet of the equivalence class of phi and that of psi is just the equivalence class of the conjunction of phi and psi, and so on and so forth. Okay? But of course, if I say that this equivalence class is equal to this equivalence class, yeah, as a logician, I would just say phi and psi is a contradiction, or the negation of phi and psi is a tautology. When I say that the equivalence class of the disjunction is not equal to the equivalence class of a tautology, as a logician, I would just say that is not a tautology. But of course, if we then unpack that definition, yeah, that means, this here means that there is no model M of my logical system S in which both sentences are true, and there is a model M in which neither of them is true. But that, of course, is again a very fancy way of saying they cannot be true together, but they can be false together. Can and cannot boil down to quantification over models of my logic. Truth and falsity are just this satisfaction relation between formulas and models. Good. Second example, power set. I want to run through this very quickly. It's very easy. Just take the power set of some set X, and then we can say, for example, of two sets S and P, subsets of X, that they are contrary relative to this power set when, well, when they have an empty intersection, but their union is not exhaustive. And now I want to show this again, because look, this is an Aristotelian diagram consisting of sentences coming from a Lindemann-Tarski algebra of a logical system, whereas this is an Aristotelian diagram consisting of single words, sets, I would say, interpretations of sets, extensions of sets, coming from a power set algebra. But we can now say that both of them are analogous to each other because they both arise from this general definition just by plugging in different Boolean algebras, different concrete Boolean algebras. Okay. Now, this is the most fun one. This is the one that I like the most, the third one. So the one that I find most exciting. So I want to show it to you. What I'm going to do now is I'm going to look at the Boolean algebra. Sorry, I'm going to look at the Lindemann-Tarski algebra of my logical system and then take the power set of that. Okay. Or I'm going to be looking at the Cartesian product of the Lindemann-Tarski algebra with itself and take the power set of that. And these are also Boolean algebras, so I'm okay to plug them in. Let's see what happens if we do that. So I take the set A, which is just a singleton set. It only contains the equivalence class of the tautology. B contains just the equivalence class of the contradiction. Now, these are two subsets of my Lindemann-Tarski algebra, so they belong to the power set. They have an empty intersection, but they do not exhaust my entire Lindemann-Tarski algebra. But that means that I can say that they are contrary to each other, relative to this Boolean algebra, of course. Okay? That means that we can now make formal sense of the statement that the notions of tautology and contradiction are contrary to each other. Okay? So people have constructed diagrams, squares of opposition, hexagons, octagons, containing metalogical notions like tautology, contradiction, satisfiability, and so on. You can see that these perfectly follow the definition. They're just a more elaborate case. Even more interestingly, consider the relation of contrariety in S, or in the Lindemann-Tarski algebra of S. I'll usually identify logics with their Lindemann-Tarski algebra. It's logical geometry, not algebraic geometry. So look at the two relations of contrariety and subcontrariety. Well, these are two subsets of Bs times Bs. So elements of the power set of Bs times Bs. And we can say that the intersection of these two relations is empty, and the union does not exhaust Bs times Bs. Two formulas cannot be simultaneously contrary and subcontrary to each other, but they can fail to be contrary or subcontrary to each other. For example, if they are contradictory to each other. But that means, of course, that the relation of contrariety and the relation of subcontrariety are itself contrary to each other. Okay, this is not paradoxical or anything like that, because of course, when I'm talking about contrariety here, it's relative to this Boolean algebra, BS. When I'm talking about contrariety here, it's relative to another Boolean algebra. Okay, so I have lifted this by taking the power set. And you might say, okay, fine, nice, but why is this so exciting? Well, I was not the first one to realize this. People in the 13th century already knew this. So Peter of Spain said, the law of subcontraries is itself contrary to the law of contraries. I didn't bother translating the Latin, but you can see here, the law, the definition of subcontrariety is itself contrary to the law, the definition of contrariety, okay, which I think is interesting. Good. So these are the Aristotelian relations and how to define them in general Boolean algebras. What is an Aristotelian diagram, formally speaking? Well, it's just a tuple, a pair consisting of a fragment F of a Boolean algebra B. Okay, so we take any Boolean algebra B and then a subset of that Boolean algebra. When we draw the Aristotelian diagram FB, we're going to draw all Aristotelian relations that hold among the elements of F relative to B. Okay, relative to B, because Aristotelian relations are now defined always relative to a Boolean algebra. Good. So for example, I can say, let's work with classical propositional logic, which basically means the Lindemann-Tarski algebra of classical propositional logic. We tacitly identify formulas with their equivalence classes. Note that I don't write the square brackets here anymore. And then we can define, for example, this square of opposition. Okay, P and Q, P or Q, not P and not Q, not P or not Q. Okay. Now, a very important notion, and here I think you see that this is really taking an algebraic turn, because we are not just interested in entities by themselves, but also functions between entities between our diagrams. The first notion that I'm interested in is that of Aristotelian isomorphism. If we have two diagrams, D1 and D2, then we're going to say that an Aristotelian isomorphism from the first to the second is a bijective function from the fragment of the first diagram to the fragment of the second diagram, such that for all Aristotelian relations R relative to B1 and all X and Y in the first diagram, we have that X and Y stand in that Aristotelian relation R relative to B1, if and only if Fx and Fy stand in that very same relation to each other relative to B2. This is absolutely what you would expect, right? And this allows us then, for example, to say that this diagram coming from, let's say, 1980s legal theory, and this diagram coming from 2010s computer science knowledge representation are Aristotelian isomorphic to each other. You can just see the isomorphism visually, I would almost say. This also allows us to study automorphisms and of Aristotelian diagrams and so on and so forth. That's not a direction that I want to explore today. Secondly, we also have a notion of Boolean isomorphism. Given that Aristotelian diagrams are always defined relative to a Boolean algebra, yeah, you also expect to be able to say something about their Boolean structure. Okay, that's a bit more subtle. So first of all, given a fragment F of a Boolean algebra B, we're going to say that the Boolean closure of F in B, denoted like so, is just the smallest subalgebra of B that contains F. And that's the natural notion of what a closure might mean. In the technical literature on Boolean algebra, this is also called a subalgebra generated by F in B. But I like to call it the Boolean closure, because this idea of closing a set off under certain operations is a very standard thing to do in mathematics. We talk about transitive closure of a relation and so on and so forth. Okay, with this in mind, we can now define a Boolean isomorphism from a first Aristotelian diagram to a second one by saying that it should be a bijective function f from the first to the second that can be extended to a Boolean algebra isomorphism H from the Boolean closure of the first diagram or the first fragment relative to the first Boolean algebra to the Boolean closure of the second fragment relative to the second Boolean algebra, where extends, of course, just means that if I take my Boolean algebra isomorphism H and I restrict it to F1, I just get F. Okay. I see there's a question. I want to do one more bullet point and then I come to your question, because I want to explain the intuition behind the definition. If it's not immediately clear why this is the definition that we really want. Well, the idea is we want to define a notion of Boolean isomorphism, so we want to impose standard requirements that any good algebraist would impose on a notion of morphism or isomorphism. I'll come to the morphisms later. I know it's a bit weird to first talk about isomorphisms and not yet about morphisms, but that's fine. And so we want to say something like, if I have x and y, it doesn't matter whether I compute their meet in B1 and then take the image under F, or I take the image of x and y first and then compute the meet in the second Boolean algebra. And that's a typical kind of condition that you want to impose. But we cannot say this because our fragment F is not closed under the Boolean operations. The fact that x and y are in F does not guarantee that their meet, that their conjunction, their intersection, is also going to be in F. So this is not even a well-formed expression, if you see what I mean, because this guy is not necessarily in the domain of F. To take care of that problem, we move to the smallest Boolean algebra in which we can say this, that is the Boolean closure of F1 relative to B1. And that's why we have this. Yeah, now your question.
Yeah, such a Boolean closure might also be interesting, for example, to do this, well, I don't know if it's interesting, when we haven't been given explicitly a containing Boolean algebra. So we just, for example, start from a diagram that's not embedded.
Oh, yes.
Can this always be done?
Yes, yes, in a beautiful way, yeah.
And then also a second one, for a Boolean algebra.
Sorry, for a finite one. For an infinite, it's more difficult. But yeah, again, in the literature, everything we find is finite.
Yeah,
so yeah.
Have a diagram that we've drawn is usually finite.
Yeah.
And for the Boolean isomorphism, we're asking now that it can be extended, but this raises the question that still it might be problematic to define things like above the conjunction of these two, because this extension is not a priori unique, or is it?
It is, yeah. I want to say next slide, but I don't know. Let's see, but it is going to be unique. Yeah, good. So yeah, can just mean there exists an isomorphism, and if it exists, it's unique, which is kind of trivial to see almost, because it's determined by, it's basically you prove that it's unique by induction on what we call formula complexity in logic. It's determined. You know what it has to do on the atomic level, if you see what I mean, very metaphorically speaking, and then it propagates upwards. Right? It's fixed on the atomic level, on the base level, because of this condition, and then it's fixed for all levels above because it has to be an isomorphism. It has to preserve all Boolean structure and reflect as well. We can show that every Boolean isomorphism is an Aristotelian isomorphism. That's pretty trivial because the Aristotelian relations are defined relative or purely in terms of Boolean operations. So if you have two diagrams that are Boolean isomorphic, they match on all their Boolean properties, and thus a fortiori on their Aristotelian properties, which formulas are contrary or subcontrary, and so on. It's not the case the other way around. Not every Aristotelian isomorphism is a Boolean isomorphism. Here's an example. So here's a fragment containing three singleton sets A, B, and C. I've drawn them for you here. So it's the same fragment, mind you. But here I consider this relative to the Boolean algebra power set ABC, and here I consider it relative to the Boolean algebra power set ABCD. Okay. The identity function is an Aristotelian isomorphism between these two, which you can see visually. They're three elements pairwise contrary to each other here and also here. But this is not a Boolean isomorphism. Actually, there does not exist a Boolean isomorphism between these two in the first place. The intuitive reason is, well, look, if I take the union of these three elements, that's going to be ABC, which is the top element in this Boolean algebra, but not in this Boolean algebra. Okay?
This does raise the question, though, for now, in the Aristotelian sense, we're looking at vertices, which are single statements, and then just connecting them, which are relations between two
Yeah.
statements.
Binary relations.
Binary relations. We could, for example, extend this to ternary and say these
Yeah.
three together in left are
Yeah.
spanning
Sure.
space, and they are no
Yeah.
longer. And then
Absolutely. A postdoc of mine, Stef Freiters, has done exactly that. Not necessarily to ternary relations, but just to arbitrary relations of arbitrariety, where you live basically from formulas to sets of formulas, and where you say of an entire set of formulas that it is contradictory or contrary, and then you say of two sets that they are contrary or contradictory to each other, if and only if their union is as a big single set contrary or contradictory, and then you can do exactly what you are saying. Yeah. Good. So we did something kind of weird from an algebraic perspective, namely we started talking about isomorphisms, be they Aristotelian or Boolean, without first talking about homomorphisms. Right? Normally you want to do it in the opposite order. I will talk about homomorphisms later. Why? Well, because we don't really, at least for now, we didn't really need homomorphisms. The only thing I'm interested in is isomorphisms for now, because I want to say of two diagrams that they are really analogous to each other, remember? And why are they useful? Because they draw analogies, blah, blah, blah. Well, homomorphism is too weak a notion to make that precise. I want to have isomorphisms. Put differently, when we construct a typology, a classification of Aristotelian diagrams, we're going to need isomorphisms, not homomorphisms. We say that an Aristotelian family is a class of Aristotelian diagrams that are all isomorphic to each other, Aristotelian isomorphic to each other, and it's maximal. So if I have a diagram in the class and it's isomorphic to a second diagram, the second one is also in the class. Okay, so a maximal class of Aristotelian isomorphic Aristotelian diagrams. But from time to time, I drop the word Aristotelian. So we say, for example, that we have the Aristotelian family of classical squares of oppositions. You met several members of that class. We have the class of the Aristotelian family of Jacobi-Sesma-Blanchet, JSB hexagons. You met some examples of that class before. The names don't matter. These just happen to be the people that first studied diagrams belonging to this family, to this class. All around the same time, 1950s, early 1950s. All without claiming that they were copying from each other, but I don't buy it. Yeah. Good. So these are the Aristotelian families. Then we have our Boolean families. Exactly the same notion, just replace Aristotelian with Boolean. So then we have our Boolean families, maximal classes of Boolean Aristotelian, Boolean isomorphic diagrams. But the point is, we know how Aristotelian and Boolean isomorphisms relate to each other, and that is going to have a direct counterpart now from this typological perspective. Remember, we said that every Boolean isomorphism is an Aristotelian isomorphism. Well, that means that the Boolean families should actually be viewed as subfamilies of Aristotelian families. If two things belong to the same Boolean family, they always belong to the same Aristotelian family, right? Because every Boolean isomorphism is an Aristotelian isomorphism, but not the other way around. Two diagrams can be Aristotelian isomorphic to each other without being Boolean isomorphic to each other. That means they can belong to the same Aristotelian family without belonging to the same Boolean subfamily. In other words, Aristotelian families can have multiple Boolean subfamilies. So for example, the JSB hexagons, the Jacobi-Sesma-Blanchet hexagons, have two Boolean subfamilies, which we call the strong ones and the weak ones. We say that an Aristotelian diagram is a JSB hexagon if and only if it contains three elements that are pairwise contrary to each other. Let me quickly show this to you. And for example, here, this guy, and this guy are contrary to each other. Similarly, here, here, and here. It's always this kind of triangle. It's also the example that I was showing you earlier, but there I didn't bother closing it off under complementation. But this would then be a strong one, and this would be a weak one, if you see what I mean. Not Boolean isomorphic to each other. This is half of a strong JSB hexagon. This is half of a weak JSB hexagon. In a strong JSB hexagon, if I take the three pairwise contrary elements, their join is a tautology, but in a weak one, their join is not a tautology, does not coincide with the top element, the unit element of my Boolean algebra. Okay. So for example, here in propositional logic, this is a strong and this is a weak JSB hexagon. Aristotelian isomorphic, same Aristotelian family, the JSB hexagons, but not Boolean isomorphic. Why? Well, look at these three formulas and compute their disjunction, and you will see that it's a tautology. That's a simple exercise in truth table logic. The disjunction of these three, however, is not a tautology. Note that the example that I'm giving you involves three formulas. That's not a coincidence. Why? Because the Aristotelian relations are, as I was already emphasizing before in the discussion, are binary relations. Okay, so everything that is at the level of just two formulas, the Aristotelian relations can capture. Anything that happens at the level of three formulas or more, they might fail to capture, if you see what I mean. The typical example in logic would be P or Q, not P, not Q. All three of them taken together are inconsistent, but if I can only look at two out of the three formulas, it's consistent. Okay, that's another example. Okay, good. What I want to do now is I want to introduce bitstring semantics, basically because I want to be more precise in what I mean with different Boolean subfamilies. And because at the moment there are two Boolean subfamilies, I call them strong and weak, but later we're going to meet Aristotelian families that have like 7 or 8 Boolean subfamilies. And what are we going to call them? Like very strong and very weak and so on. So I want to have a better naming system, if you see what I mean. Okay, and that's where bitstring semantics comes in. Bitstring semantics is a systematic way to assign bit strings, that is elements of the sequences of zeros and ones for some finite number n, to the elements of your Boolean algebra. If we take the Boolean algebra B to be finite, then this is also always going to be finite. We can do this. So in a sense, nothing spectacular is happening here. This is just a representation theorem for finite Boolean algebras, which says that every finite Boolean algebra is isomorphic to a power set of a finite set. And instead of looking at the subsets, I look at their characteristic functions, you could say. Okay, good. However, the perspective is slightly different because we don't start from a Boolean algebra. We start from an Aristotelian diagram, which of course contains a Boolean algebra, but the more important part is really the fragment, if you see what I mean. The Boolean algebra you're just carrying around with you to be able to define the Aristotelian relations holding between the elements of your fragment. And which is again a question that was already raised. This could be interesting if you just have a fragment and you don't know what your underlying Boolean algebra is. So, given a diagram FB with a fragment F, a finite fragment F, and a Boolean algebra B, the partition induced by this fragment in this Boolean algebra consists of the following meets. So you just take the meet computed in the Boolean algebra B of all of these elements or their negations. So plus minus just means X or not X. So for example, if I have 3 elements, then how many, if I have 3 elements in F, then how many elements do I need to consider in the partition? 8, 2 to the power 3. If they are A, B, and C, I have to look at A and B and C, A and B and not C, A and not B and C, A and not B and not C, and so on and so forth. And I throw out the ones that are inconsistent. Okay? I throw out the ones that are inconsistent that coincide with the bottom element of my Boolean algebra. We call this a partition because it has all the properties of a partition, an ordinary partition in mathematics, namely its elements are mutually exclusive and jointly exhaustive. Jointly exhaustive here means that the join of this partition is the top element of my Boolean algebra, and if I compute the pairwise meets of these elements, it's always the bottom element. In terms of, if this is not just an arbitrary Boolean algebra, but a power set algebra, I'm saying here A intersect A prime is empty, and the union of all of the cells of the partition is the entire thing. So it's a partition, as we know and love in mathematics. Good. We can now prove that any element y in the fragment, or actually in the Boolean closure of the fragment, can be written as the join, the disjunction, the union of all the elements A in the partition induced by the fragment that are below y. Okay? What we then do is we fix an ordering on the elements of the partition, A1 through AN, so that we can refer to these elements by their number. And then we say that for any element y in the Boolean closure of F, we define the bit string to be a sequence of n bits, n times 0 or 1, by saying that in the ith bit position, I'm going to put a 1 if the ith formula in the partition, and this is why I needed to fix an ordering, of course, because I now want to say AI, the ith formula in the partition is below y, and 0 if it's not below y, but you can prove that it is actually equivalent to it's below not y. And that's what you see here. That's not too important. And then you can prove that this, going from the Boolean closure of f in B to 0, 1 to the nth is a Boolean algebra isomorphism, and thus also, of course, an Aristotelian isomorphism. Good. Yeah, I have some results that correlate fragment size and bit string length, but I want to skip those. They're not super important, but good. This is more important. We can use our bit string semantics, in particular the length of the bit strings, to differentiate between Boolean subfamilies. So, for example, let's return to the JSB hexagons. I defined strong and weak JSB hexagons in terms of, well, the join of the three pairwise contrary elements is or is not the top element of your Boolean algebra. We can do the exact same thing in terms of their bit string length. If I have a JSB hexagon, then I can say that's going to be a strong one if and only if the partition induced by that diagram in that Boolean algebra has 3 elements. In other words, I need bit strings of length 3 to encode it. It's going to be a weak one if I need bit strings of length 4 to encode it. So for example, here you see the 2 diagrams from before. This is a strong one, this is a weak one. I already explained why this one is strong and this one is weak. Another explanation for the same thing is I can say, well, now, compute the partition induced by this diagram, by these 6 formulas, and you're going to see it's this one. It contains 3 formulas, alpha 1, alpha 2, alpha 3, whereas this one contains 4 formulas. Okay. In terms of bit strings, let's take an interesting example. For example, this one, P or Q. Well, P or Q is basically the disjunction of P and Q and P exclusive or Q, which is what it says here. So I put 1, 1, 0. 1, 1, 0. I need bit strings of length 3 here. I need bit strings of length 4 here. Let's return to the original characterization. Let's compute the join of these 3 elements, 1, 0, 0, or 0, 1, 0, or 0, 0, 1. That is 1, 1, 1, which is the top element of 0, 1 to the third. By contrast, if I compute these guys, the join of these guys, I get 1, 1, 0, 1, which is not the top element of 0, 1 to the fourth. Good. So that means that I can now identify Boolean subfamilies with bit string lengths, if you see what I mean. I can just talk about no longer the strong and the weak JSB hexagons, but those that correspond with length 3 or length 4. If we restrict ourselves to a special kind of diagrams, sigma diagrams, that are diagrams that do not contain top or bottom elements and that are closed under negation or complementation, if you want, which are the most common ones that we see, the square, the hexagon, the octagon, and so on, then we have the following results. So there is exactly one Aristotelian family of sigma 0 diagrams, the empty diagram. There is exactly one Aristotelian family of sigma 1 diagrams, 2 families of sigma 2s, 5 of sigma 3, 18 of sigma 4, etc., etc. You can read the slide. Okay. We also know the Boolean subfamilies up to here, but not beyond. Okay. In an overview, I call this the periodic system of logical geometry. What do we see here? Well, we see all the sigma diagrams. So basically, empty diagram, 2 formulas, 4 formulas, 6 formulas, 8 formulas, and so on. But instead of 8, I should say 4 pairs of formulas because of closed under negation. And here you have all the bit string lengths. Note, first of all, that there's a lot that is blacked out, that is in gray, because of these results on the slide that I skipped, with the correlation between bit string length and fragment size. This is going down logarithmically. This is going down exponentially. And then you see that, for example, with the sigma 3s, that is the hexagons, you see here JSB has 2 Boolean subfamilies corresponding to length 3 and length 4. These are the strong and the weak ones. But you see, for example, that there is also such a thing as a U12 hexagon. I won't bother you with the details, but it has a total number of 5 Boolean subfamilies. But we can now nicely classify them by just saying, well, they correspond to, do I need bit strings of length 4, 5, 6, 7, or 8 to encode them, to represent them? Good. This is what I absolutely wanted to tell you. I'm happy. Everything from now on is bonus. I now have 2 sections on logic sensitivity and bitstring semantics on the one hand, and on category theory on the other hand. Are you guys familiar with this quote about birds and frogs in mathematics? Okay. So Freeman Dyson said there are 2 kinds of mathematicians, birds and frogs. Birds fly high in the air and survey broad vistas of mathematics out to the far horizon. They delight in concepts that unify our thinking and bring together diverse problems from different parts of the landscape. Frogs live in the mud below and see only the flowers that grow nearby. They delight in the details of particular objects and they solve problems one at a time. Why did I bring this quote? Well, this is a frog problem and this is a bird problem. I don't have time for both. I let it to your wisdom. I leave it to your wisdom, like, what do we do? I'm up for either. How are we doing on time? How much time do we have left, more or less?
8 minutes.
8 minutes, okay. Okay, categories, okay, good. Well, obvious starting point. We have objects, Aristotelian diagrams. We have arrows, Aristotelian and Boolean isomorphisms. I already put the iso between brackets. So this kind of begs for a study in terms of category theory, right? 2 theoretical desiderata that we have are, on the one hand, continuity with existing work. For example, we're going to get the notion of isomorphism in our category of Aristotelian diagrams. We want it to coincide with the notion that we already had and that we defined and introduced for classificatory purposes. On the other hand, we also have a more internal looking, if you want, desideratum, namely we want the categories that we construct to have a rich internal mathematical structure. Then we're going to be talking about, for example, do we have initial objects? Do we have terminal objects? Can we compute products or in general limits and co-limits? What about links with other categories, sets, Boolean algebras, and so on? Okay. I'm going to start with the Boolean, not with the Aristotelian. There's a very good reason for that. I'll come to it in a minute. I'm going to start with the Boolean isomorphisms and generalize them to Boolean homomorphisms. Okay? This is the definition of Boolean isomorphism from before. This immediately suggests the notion of Aristotelian homomorphism, right? So we say that a Boolean homomorphism from one diagram to a second is a function, no longer necessarily required to be bijective. We drop that. That extends not to a Boolean algebra isomorphism, but to a Boolean algebra homomorphism between the 2 Boolean closures of the respective diagrams. Note, by the way, now I need this. If it extends, the extension is unique. To come back to a question that was asked before, and the extension will be written F bar. Okay. For example, if you go from right to left, that's a Boolean homomorphism. If you just take the bit strings of length 4 and you cut out the 3rd bit position, and then you go, for example, from 1011 to 101, you cut out the 3rd bit position, that's a Boolean homomorphism because it extends to a Boolean algebra homomorphism on the Boolean closures. You cannot go from left to right in a Boolean homomorphic way. Okay? You can go from the high bit string length to the low bit string length, but not in the other way. There's an argument for that, but I want to skip that because I only have 8 minutes, actually even less now, but I'm going to say 8. So if we take the Aristotelian diagrams and we equip them with the Boolean homomorphism defined in the way I just did, they give rise to a category. I assume you all know more or less what that means, so I'm not going to go over all these individual bullet points. The isomorphisms in this category are exactly the isomorphisms from before, so that's very good news. Okay. The categorical notion of isomorphism in terms of, well, homomorphism, and there exists a second one, so that the 2 compositions are identity functions. I shouldn't say functions. Corresponds to the notion from before. Good. we, and when I say we, it would be really unfair not to mention the name of Alex de Klerk, who is a PhD student who just started working on exactly this. Know already some stuff about the structure of this category. We know what its terminal objects look like, its initial objects, and we also have a functor from this category of Boolean, from this category of Aristotelian diagrams with Boolean homomorphisms to the category of Boolean algebras. What does it look like? Well, it takes an Aristotelian diagram FB and it maps it onto the Boolean closure of F in B. And it maps any Boolean homomorphism from a diagram D1 to a diagram D2 to this uniquely existing, here uniqueness is important because otherwise this would not be well defined, to this uniquely existing extension of F defined on what is CL? Well, literally the Boolean closure of the diagram. Vice versa, we also have a forgetful functor from Boolean algebras to Aristotelian diagrams, and it's basically a diagonalization. If I have a Boolean algebra, I know what to fill in the second coordinate. What do I fill in the first coordinate? Just B itself. That can happen. We take F to be the entire Boolean algebra. These two form an adjoint pair. Okay, I'm like taking very big. I'm doing bird mathematics now, not frog mathematics. Final thing that I want to say is, what about the Aristotelian homomorphisms? Because I first talked about Aristotelian isomorphisms and Boolean isomorphisms. You might say it's weird that you now start with the Boolean. Why not start with the Aristotelian? Because here the situation is a bit more subtle. Okay. The definition of Aristotelian isomorphism once again suggests an obvious notion of Aristotelian homomorphism. And we say that an Aristotelian homomorphism from one diagram to a second one is a function no longer necessarily required to be bijective, such that for all Aristotelian relations, if x and y stand in the relation relative to B1, then fx and fy stand in the relation relative to B2. So we have weakened if and only if to just if then. Structural preservation, not necessarily reflecting your structure. This is the obvious notion. There are some examples, but I don't really care too much about the concrete examples. It's more important to give you the big picture. They once again constitute a category. Aristotelian diagrams, together with Aristotelian homomorphisms defined in the way I just did, constitute a category. The isomorphisms in that category are the ones that we know from before. So that's good news for the category. Okay. The category has initial objects, so rich internal structure. Remember, the second desideratum is there. Yay, good news. I can define some further categories and again introduce an adjoint pair of functors, which is also very nice. Good news. I'm summarizing. But now comes the bad news. This category does not have terminal objects, does not have products, and so on. And remember, every Boolean isomorphism is an Aristotelian isomorphism. We would expect then that every Boolean homomorphism is going to be an Aristotelian homomorphism. That's not the case. Bitstring, bit position deletions, like going from ABC to AC, that is a homomorphism, that is a Boolean homomorphism, but not an Aristotelian homomorphism. For example, because these two elements are contrary to each other, these two are contradictory. So you don't preserve the relation of contrariety. But we have a solution. We have another notion of Aristotelian homomorphism, which we call infomorphism. Yeah, here, infomorphism, increasing infomorphism. I don't want to go into why it's called increasing infomorphism. It can actually be viewed in a purely algebraic way, as in structural preservation of a certain number of relations. It's just that the relations look a bit weird, but that's in principle fine. And with this notion, you do have only good news, I would say. They constitute a category. The isomorphisms in this category, lo and behold, are exactly the Aristotelian isomorphisms from before. So this is really interesting. We have two different notions of homomorphism. At the level of homomorphism, they don't coincide with each other, which is what we want, because the first one was not the right one. So we tried to repair it with a second one. We really want it to be a second one, a new one. But at the level of isomorphisms, they are the same. The notions of isomorphism that they give rise to are the same. Now we can show that every Aristotelian Sorry, we can show that every Aristotelian homomorphism is an increasing infomorphism, but not vice versa. So this is the diagnosis of the problem. Why was the category not well behaved, or not as well behaved as we would have liked? We didn't have enough arrows. We introduced a couple of more arrows in our category, basically. Now we can show that every Boolean homomorphism is an increasing infomorphism, just like every Boolean isomorphism is an Aristotelian isomorphism. This category has terminal objects, has initial objects, has products, the same as in the category with the Boolean homomorphisms, by the way, and again, an adjoint pair. And there is much more to be said, but every bird at some point has to land. So, thank you.